It's a pleasure for me to be here. Thanks to Maria and Camille for inviting me to participate in this PhD school. And they've asked me to give you the basics, the fundamentals. So hopefully I've aimed correctly. I'm sure that some of the material I'll be presenting you've seen before, but I think it will set the stage for the more advanced lectures you'll have during the week and probably refresh your memory about Darcy's law, hydraulic head, because these are concepts that we are commonly or constantly using. I'm just showing here two types of porous media. Glacial deposits, that's an outcrop in a quarry in Quebec City. If you're at the back, you might not see that well, but it's very heterogeneous. You see some boulders at the bottom, there's some finer material at the top, so material ranges from clay till to boulder size grains here. So very heterogeneous. And then we have fractured limestone, which is also heterogeneous but has some regularity. So the fracturing is systematic, horizontal, vertical. We have some microfractures. We have a porous matrix. It's not an easy material to work with or to represent, but it's, I would say, much easier than crystalline bedrock, where the fracturation is much more, I won't say random, but much more complex, much more irregular. So when we try to represent these systems with some type of continuum approach, we have challenges. So today I will be covering porous and fractured materials, only fully saturated single-phase flow, because you have lectures about multiphase flow and unsaturated flow systems later on in the week. I'll just have a comeback, a review of porous medium, the scale of description, the properties. Of course, I will cover again Darcy's law. That's the basic relationship that we use in hydrogeology. Hydraulic head, I will hopefully briefly show equation of continuity, not go into too much detail, and then I will cover fractured media with various concepts that exist to represent them. I'm not focusing on the pore scale here. I'm going to be above the pore scale. I know that some of you probably are interested in pore scale processes, and I think that again, there might be some presentations later on in the week. The applications that I'm working on, I haven't presented myself, but I do a lot of model development, model application in coupled surface water, groundwater flow system, typically with the model hydrogeospheres. So we do simulations for various types of catchments or watersheds to look at the water system as a whole. So we don't really work at the pore scale, we work at larger scales. Just to mention Interpore, this network that probably some of you know, some of you belong to that network. I just here have a list of the topics that are covered by this network, and of course it's a network that is focusing on porous media. Like I said, I'm more focusing on natural systems, geological systems here, but it can range from, if you look at here, food, paper and textiles, filters, foams, membranes, fibers and composites. So it's a very, very wide area, the porous media world, and again with interest at the pore scale, but also at larger scales. But like I said, I will not cover the pore scale too much here. We have various scales of descriptions that can be proposed. This is my friend Alain Dessag in his recent textbook, who proposes the various scales from the micro scale, the pore scale, to the macro, that would be like a lab sample column in the lab. The mega scale would be something in the field, if you're looking at a small catchment or a small site, and then even the giga scale, which would be a much larger catchment. And of course, as soon as you go from one scale, smaller scale to the other, you have some homogenization that is required, or some averaging of properties, because you cannot represent everything that exists at the smaller scale when you move to a larger scale. So you introduce some new parameters. Of course, the concept of representative elementary volume is central to this upscaling, and that's what we use to go from a discontinuous system to a continuous or continuum approach. Again, that's something you might have seen before. This is from Baer and Bachmat, where we have here the typical property is porosity on the vertical axis, and this is the size of measurement or of observation. So if you go to 0, the very small size, you're actually at the pore scale, and your measurement location could be a pore. and the porosity is 1. It could be a solid grain, non-porous, the porosity is 0. And then as you increase the size of your observation, you start having values that eventually reach the porosity of this equivalent porous medium at no longer the microscopic scale, but at the larger scale. So this is where we would be working when we leave the pore scale. And that allows us to represent these discontinuous pore scale system as a continuum. That's what we are working on using the RAV concept. And the same thing for velocity, not only the properties, but the fluid flow. At the pore scale, we might be able to represent all these individual flow paths, but we replace that by an equivalent, say, equivalent specific discharge or Darcy flux, which is what we use. It could be an equivalent velocity, groundwater flow velocity, which is then used for transport representations. And we then leave the pore scale. In a fractured system, it's the same concept applies, but typically I won't say it's more tricky, but we have more heterogeneity. This is again an example from taken from the book of Alain Dassargues. So we've got here a fractured system, and we see sets of fractures. We have fracture zones here. We have a matrix that might be porous. Not all rock matrices are not porous. Some are porous. And we start with the smaller scale of description. We are here in the sub-REV scale. We're in the matrix. Then we might reach some average value. And as we go larger and larger, we start to incorporate more heterogeneity. And we might be able to end up here with another REV for a large enough here area that includes all the various discontinuities that we have in this rock formation. But we could, this is one example where we would try to define an REV or a continuum for a system that is obviously heterogeneous, but as we'll see in the fractured porous media representation, we could also have a combined approach where we would represent the matrix here, the porous matrix, as a continuum, and then we might want to represent these discrete fractures implicitly in the model, or represent the set of fractures here as another continuum, which would be a fractured medium. So that would be some type of dual porosity approach. Good. Porosity is simply defined as the volume of pores over a total volume for the porous medium. If we take the case of granular material on consolidated deposits or glacial deposits, like I showed at the beginning, porosity highly depends on the grain size distribution. So this would be a fairly uniform grain size distribution. This would be a non-uniform grain size distribution with some finer particles that plug the porosity, so porosity decreases. We might have here some grains that are themselves porous, so we have two porous systems, the pores formed by the assemblage of grains, and then the grains themselves are porous. Or we could have some filling here of the porosity as the rock, as the deposit basically becomes cemented. For fractures, these are simple representations here. Again, some concepts are are shown here. This comes from Kruzman and de Ridder. So this is a block of rock with regular fracturing. So we kind of guess here that there's a fracture network with horizontal and vertical fractures, some dead-end fractures, and some continuous fractures. And here we can assume that the matrix is not porous or impermeable. If we're in crystalline rock has a very, very low permeability and low hydraulic conductivity, often assumed equal to be 0. We could have superimposed on the larger fractures some microfractures that might come from some tectonic process, some ground movement, and so on. So we would have two sets of fractures, what is called the microfractures here. And then the other case here would be indicated with the little dots, the matrix could be porous. So we have fractures, for example, in sand units, in sandstone units. We have some aquifers in Quebec, for example, sandstone aquifers that are fractured, and the sandstone itself can be very porous. Or there's some chalk aquifers in Northern Europe. The chalk is very porous and is fractured, so it would be a system of fractures and porous matrix. We also define very often different types of porosity, and let's say that the nomenclature in the various textbooks or papers I don't think is uniform, so that might lead to some confusion. When it comes to fluid flow, some people define the effective or dynamic porosity, because not all the pores participate equally to fluid flow. There might be some dead-end pores. This would be an example here. This is very hypothetical, but let's say we have general groundwater flow direction from left to right. We might assume that these non-continuous fractures don't participate too much to fluid flow, but this fracture here probably conducts a lot more flow. So we might have some, when we look at the flow processes, not all the pores participate in the flow, so we often use, like I said, effective dynamic porosity. Or when we are interested in drainage, near surface drainage of the water table, we also use a drainage porosity, which is equivalent to the specific yield. Darcy's law, briefly go over it again, that was developed in 1956 by Henri Darcy, who was an engineer working in the city of Dijon here in France. And he wrote a very extensive book, more than 1,000 pages, where he described various things, including description of experiments he made, where he basically infiltrated water into a soil filled with typically sand, and came up with relationships. The relationships was that the volumetric flow rate is equal to the head difference between the inlet and the outlet, and the head difference was given by the elevation plus the pressure in a manometer here. So we already introduced the concept of hydraulic head without really defining it. So the head difference is directly proportional to the volumetric flow rate. The volumetric flow rate, all other parameters being kept constant, is inversely proportional to the length of this column, and it is finally proportional to the area, the cross-sectional area of the column. He then arrived at this empirical relationship, so there's an equality, there's a need for a constant of proportionality, which is K, which was defined as the hydraulic conductivity. Hydraulic conductivity as units of 1 over length equal to velocity, but it's not a velocity, it's a property of the system. So that's Darcy's law, and I showed all these different topics that are included or looked at by Interpor. Darcy's law is used in all kinds of other areas as well. So that's the same type of relationship to relate the flow of fluids to some head difference or some energy difference. Hydraulic conductivity can be defined in words as the ease with which water can flow through a porous medium. And it actually depends on the properties of the porous medium, the permeability, and the properties of the fluid density and viscosity, rho and mu. In hydrogeology, we often assume for most applications that porous density and viscosity are constant. So there's a tendency that people tend to use permeability and hydraulic conductivity to define the same thing, but we should be more consistent and use hydraulic conductivity to define this parameter that goes into Darcy's law and keep permeability for the porous medium. I say that because, again, in some textbooks or some papers or reports, you see people writing permeability when they should really be writing hydraulic conductivity. But for most applications, we only work with hydraulic conductivity, but if you're interested in multiphase flow, then you basically work with permeability and not hydraulic conductivity, because you have variable then one. Well, 0 is You will not get 0, it might be some fractions of a percentage. To 1, it's not 13 orders of magnitude. And when I talk to my colleagues in structural engineering, I show them that, they would be shocked because they work with man-made material, and for them variability is something that almost does not exist. So that's something to keep in mind. And also when we try to go from a discontinuous system to a continuous to get some properties, we have challenges with hydraulic conductivity. Darcy's law can be expanded in 3 dimensions. So if you do some numerical modeling, you will use Darcy's law in 2 or 3D. I just show here in the industrial form, we have a relationship between again, Q is either specific discharge, Darcy flux. Some people use specific velocity, but it is the term that comes from Darcy's law. It's a vector, and in 3 dimensions, it has 3 components. The hydraulic gradient also is a vector, has 3 components in 3 directions. So we have here in matrix form Darcy's law, the 3 components of a specific discharge, the 3 components of the hydraulic gradient. And we have to introduce the quantity that relates to vectors is a tensor. So hydraulic conductivity is really a tensor in 3 dimensions with 9 components, not necessarily symmetric. And if we just expand the first line to show the component of the specific discharge in the x direction, it's kxx times delta h delta x, so gradient in the x direction, kxy delta h delta x, kxz delta h delta z. And we have similar expressions for the y and z directions. So we kind of have an idea what hydraulic conductivity is. We can visualize hydraulic conductivity, but it's kind of hard to visualize what is the component of a hydraulic conductivity tensor. So we cannot measure it, we cannot see it. What I say is that because we have a 3D gradient that might be oriented in some direction in space because of pumping, because of recharge, we have Darcy flux that might be oriented in a different direction because water flows more or less easily along some directions and not necessarily along the direction of the gradient. So we can look at, for example, the kxy component of the hydraulic conductivity tensor is the component of hydraulic conductivity that generates flow in the x direction, qx, given a component of the hydraulic gradient in the y direction, delta h delta y. And I would say that in practice, we have these expressions that exist, 3D, fully general Darcy's law, but in practice, I'm not aware of too many people who go get these components of the hydraulic conductivity tensor. One example where you could get them is a very simple example that, again, you might have seen in textbooks. A simple 2D layered system, so 3 layers of uniform thickness, but different, with the considered homogeneous K1, K2, and K3. Total thickness is B. If you apply Darcy's law and you assume steady state flow, either vertically across the layers or horizontally along the layers, you get equivalent relationships, kxx prime, kzz prime, that depend only on the hydraulic conductivity of the layer, the thickness of the layer, and the total thickness. So you replace this layered system by an equivalent system. So this is some type of averaging here that we're doing, upscaling. You get only now 2 hydraulic conductivity values. You have this block now is homogeneous but anisotropic. And if your system of coordinates x and z is oriented horizontally and vertically like we have here, it's oriented along the principal directions of hydraulic conductivity, then Darcy's law simplifies to this here. The off diagonals become 0 and we only have the principal components of hydraulic conductivity. So we then can express qx and qz knowing these principal directions that we would get from these relationships. And that's something actually some modelers will do. They know they have a layered system, could be sedimentary layers. The model is at the larger scale. They still want to incorporate the effect of the different layers, but not discretize every layer in the model. They will homogenize, get the equivalent properties, and use these properties in their model. Darcy's law is, for most cases in hydrogeology, is considered valid. We don't really check if Darcy's law is valid because flow velocities are very low, typically in groundwater flow system as opposed to surface water flow systems. But we typically we assume that there's an upper limit of validity that can be checked with by computing the Reynolds number. So we have here the specific discharge or Darcy flux as a function of hydraulic gradient. So if the gradient becomes very large, you might, and the Reynolds number becomes typically over 10, the relationship between discharge and gradient is no longer linear, and you see here a non-Darcian behavior. That would be for systems that are very, very permeable. Typically would be a karstic system where there's people who have proposed modifications to Darcy's law, basically have an exponent for the hydraulic gradient because the relationship is no longer linear between discharge and hydraulic gradient. And for other people who are interested in super low hydraulic conductivity material like clays, they might see a threshold effect. So even if there's a gradient applied to the clay, there's no flow. But very challenging to measure any flow in the clay, even with some gradients. But again, for most practical applications in groundwater hydrogeology, we assume that Darcy's law is valid. And finally, a groundwater velocity. It's, well, the specific discharge as unit of velocity, length over time, but it is not the velocity of groundwater in a porous medium. We have to divide by porosity because we've replaced, when we went from a discontinuous to a continuum approach, we basically use the whole volume of porous medium, but water only flows through the pores, so we have to correct for the area for flow by dividing by porosity. And as I've said, some people might not divide by the total porosity, but in some specific cases might divide by the kinematic or dynamic porosity, so which would be lower than the total porosity. Again, I'm going through this fairly quickly. Some of you have seen this material, and others who have not seen it, well, I have a couple of suggested references in the end. Okay, Darcy introduced the concept of hydraulic head because he saw that there's water moves in response to a pressure gradient, water move in response to an elevation gradient, so because of gravitational forces. But he did not define it, I would say, more rigorously. And if you're interested in not the basic, but the initial definitions of hydraulic head, that were done quite rigorously. M. King Hubbard in 1940 in the EOS Transactions of the American Geophysical Union wrote Theory of Groundwater Motion, where he presents a detailed quantitative definition of groundwater energy, and he presents a rigorous definition of hydraulic head. It's actually very comprehensive. It's not a paper, it's almost like a mini book. If you're interested in the history of groundwater, I suggest that you take a look at that article by Hubbard. But basically, he said that water moves because there's a difference in potential or of energy between a region of high energy and region of low energy. And like I said, intuitively, Darcy knew that the pressure played a role, gravitation played a role, but Hubbard put it in more formal words. There's other derivations that have been proposed to others, but here I just show that, the concept of energy is the capacity of a system to perform work, expressed in joule or Newton times meter, and work is a product of a force. Force is mass times acceleration exerted over a distance. So he used these concepts, and he said that we have energy of this groundwater, only consider the mechanical portion of energy, assume that other forms of energy, thermal, electrical, and chemical, are negligible for most groundwater flow systems. For some specific cases, they might have to be accounted for. And he came up with some relationships. Here I'm just showing the energy per unit volume of water. I won't go into too much detail, but basically he identified the three components: gravitational energy here, mgz divided by the volume. Pressure energy, actually it's the pressure, it's the energy per volume, is the pressure of the fluid, and energy associated with fluid movement. So basically he worked out energy, or the work required to move a mass of water from an elevation z equal to 0 to some elevation z. The pressure required, or the work required to increase the pressure from some value, initial value P0 to value of P. And then finally, what is the work required to move a particle of water from a velocity of 0 to a velocity of V. So he came up with general relationships. And then we have various forms. We can express the energy per unit volume, per unit mass. And the last one here that I will come back to with the next slide, is the energy per unit weight. So you divide by the weight of water, m times g, and you get three components: z, which is some elevation, pressure divided by rho g, and then velocity squared divided by 2g. So if you know the definition of hydraulic head, you already start to recognize the practical definition that we use. So it's basically energy of water per unit weight. And this is the case where the fluid is assumed to be essentially incompressible, so pressure is not a function of its density. We can further simplify by neglecting the kinetic component, because groundwater movement is very slow, so its contribution to total energy is negligible. So we really have two contributions: the pressure and the gravitation. So this is the hydraulic head as we know it. It's the elevation head plus the pressure of the fluid divided by rho g. If we have a reference fluid with a constant density, which is the case for most applications in hydrogeology. So we assume that the density of groundwater for our applications is constant. It's not always the case. If you're interested in, say, saltwater intrusion, like in coastal areas, you're going to have variable density of the fluid. If you're interested in thermal applications, geothermal, the density of the fluid will not be constant, and also the viscosity of the fluid will not be constant. So this simplification you should not make. You should not work with a reference fluid, because the fluid has variable density and potentially viscosity. But what we do is we have a reference fluid, and we define H sub P, which is the pressure head, and finally end up with this very simple expression: hydraulic head, which is the energy of groundwater per unit mass, is equal to the elevation head plus the pressure head. And that's what we measure also in practice, because how do we measure it? We drill piezometers, we drill wells. This is a cross-section that shows ground surface. This would be, say, a piezometer open at the bottom. This is the measurement point. The elevation head is the elevation of this point with respect to a reference elevation, which is arbitrary. We pick it somewhere, but we have to be consistent. If we compare two measurements with one with another, we have to have the same reference elevation. And then the pressure head is simply the fluid pressure at that point, which is shown by the height of the water column in the piezometer. So it's basically this here. And when we go out in the field, what we measure is the depth to water in the piezometer if we have a manual measurement. Otherwise, with a pressure transducer, we would measure the pressure. And we use these measurements to convert back to the hydraulic head. And that is an indication of the energy of water. I'll quickly go now through the derivation of the continuity equation, and it's basically the approach that is used in continuum mechanics. I will try to go quickly because it's early and too much mathematics, it might not be good this early. But just the basic concept, we want to define basically a mass balance for the equivalent of a representative elementary volume. So we have here our porous medium that is discontinuous, that we represent with this representative elementary volume that has uniform properties, porosity, hydraulic conductivity. And the equation is basically a statement of mass balance. We will assume that there's groundwater flow movement through that porous, that REV, and we will find relationships, expressions that provide the mass flowing in minus the mass flowing out, and we will equate that to another expression, which is the change in the mass stored in the REV. For steady state conditions, steady state means that there still is flow movement, but the mass in is equal to the mass out, and there's no change in mass stored. So don't confuse steady state with equilibrium, with a static condition, sorry. No, steady state means there's still flow movement. So we use the definition of the mass flux of a fluid, represented by the letter J here. So in words, the mass flux is the mass flowing across some area per unit time. And we define it quite simply by multiplying the fluid density rho times Q, the Darcy flux or specific flux. So if you look at the definition, it might be weird that you would multiply these two quantities and get the mass flux, but the fluid density is the mass of water over the total volume of the water, and the Darcy flux is the volume of water flowing across a unit area per unit time. So you end up with multiplying this rho times Q with the mass of water flowing across a unit area for unit time. So we compute expressions for the mass flux entering and leaving this volume. And these are, I won't say hypothetical, but they're general expressions. We don't put any numbers. So we say that J sub x here is some mass flux crossing the left face of the volume. And the mass flux leaving is the same J sub x entering the left, plus some variation, delta djx. So we leave general expressions. We can then write that mass rate. We multiply by the area of the left and right face, which is delta y delta z. So we have that here. So the mass flux multiplied by the area entering minus the mass flux, which has this variation djx times the area. So both two terms cancel out, jx times the area. So we're left with this variation of the mass flux times the area. We multiply by dx, divide by dx, so this gives us the volume. So we have an expression here for the variation in the mass flux, basically the mass rate in minus the mass rate out along the x direction. We do that for all three directions. The net rate of mass accumulation in the porous medium is given by this expression. So we have the variation over time of the density times the porosity times the volume. I should have worked out the definition of each unit, but if you do it, you will get an expression which is the mass over time. So we have the density, which is the mass of water over the volume of water, the porosity N, which is the volume of voids, which are fully filled with water divided by the total volume, and dx, dy, dz is the total volume. So we end up with, we divide by t, we end up with this expression represents the mass, the rate of change of mass of water stored in the volume over time. And then we have the final equation. We have our three terms that represent mass in minus mass out in x, y, and z directions. Has to be equal to the change in the mass stored. At the limit, we assume that our REV is infinitely small, so we go from difference equations here to derivatives, partial derivatives, so minus partial derivatives of each flux in the x, y, and z is equal to the derivative of the fluid density times the porosity over time. So we've done a few simplifications here, but keep in mind, again, that's what when I show these equations, just remember that those three terms represent expressions for the mass flowing in minus the mass flowing out across all six faces of the REV. And the term on the right is the change in the volume or mass of water for the same volume. If what flows in is equal to what flows out, the term on the right-hand side should be equal to 0. But there is still water movement. Yes?
Sorry, you said this was steady state, right?
No, this is transient.
Oh, never mind, sorry. I missed that.
Yeah, this is...
Why is there a teacher?
Yeah, perhaps I said if it's steady state, then this last term on the right would be 0. But there's still movement. But we don't have any change in mass accumulation in the volume. I'm just showing here some different notations that are used for this equation, because depending on the textbook, you might see people using initial notations, vectorial notation to show exactly the same thing. J, which is the flux, is a vector. It has three components, jx, jy, jz. The divergence of a vector mathematically is expressed by this summation here. So flow equation can therefore be written as minus the divergence of the vector j with three components is equal to the right-hand side. It's exactly the same equation as the previous slide. Just to make things more complicated, some people like to use the nabla operator, the inverted triangle. It's a vector defined by three components, delta, derivative over x, y, and z. The scalar product of two vectors, so the nabla scalar product of j is going to be two vectors here, and again we get the same expression. So some people like to write the equation that way, minus nabla times j. But it's exactly the same equation, but different notation. So if I go back to the equation, no matter what notation, it doesn't except for porosity and density on the flow side, it doesn't really contain quantities that we can easily measure. We don't really measure the Darcy flux. We don't really measure the mass flux. So we have to simplify to get measurable quantities in our equation. And what do we measure in hydrogeology? Hydraulic head. So that's something that we should have in our equation, because that's the energy of water. So we start to simplify, replace the Darcy flux J by rho Q, density times the specific discharge. So we can again write the equation in a simplified way using different notations here. And we further simplify by using Darcy's law. So we replace here the specific flux by the Darcy's law's expression. And this would be the equation in general 3D. We have indices ij that range from x, y, and z. So we would have the 9 components of the hydraulic conductivity vector in our expression. So we have hydraulic conductivity, and we have the gradient here, hydraulic gradient, in the x, y, and z directions. We further simplify because in classical hydrogeology we work with specific storage, which does not appear in the equation. So the equation has been simplified to say that this derivative here of density times porosity is approximated by the density times the specific storage of the porous medium times the derivative of the hydraulic head over time. If you are more into petroleum engineering, remember talking to someone who was in that area, and I was showing that this is what we do in hydrogeology. He was quite shocked. Why do you do that? Well, it's because we have specific storage. Oh, what is this? In some fields, they will basically have relationships for density as a function of pressure, porosity as a function of pressure, and they will not make this simplification. We could still do it in hydrogeology because these relationships exist, but we like to work with specific storage. And from a numerical point of view, unfortunately, if we do that, we differentiate here. It's actually like a chain derivation. This is a chain derivation, and we end up with an expression that does not conserve mass, because porosity and density are continuous functions, but anytime you do numerical modeling, you never work with continuous function. You represent those functions by some approximation that are not continuous. And if your discretization is not sufficient, you will start introducing mass conservation problems. You do not conserve mass. So, but that's just an aside. So the specific storage, it's a property of, yes?
So what does it physically mean in this storage term? Is there a physical meaning of this term?
Yeah, the specific storage, yeah, it's here. That's the definition of specific storage. It has units of 1 over length. And it has 2 components. Actually, it represents the compressibility of the porous medium and the compressibility of the fluid. So the first term, it's rho g alpha. That's the compressibility of the porous medium. Alpha is defined as the porous medium compressibility, has unit of inverse of not pressure, inverse of stress. And the second term, rho g and porosity times beta, that's the compressibility of the fluid. Beta is the fluid compressibility. The fluid compressibility, we say that we assume it's incompressible, and it is not, water is not incompressible, but it has a very, very low compressibility, say compared to air. So we often neglect it. So this second term here, we can say it's 0, and we only consider the compressibility of the porous medium. And every porous medium has some compressibility. If you apply a force to it, the medium will compress. And I don't have a slide on that, but basically the definition of the alpha here is the change in the volume of porous medium for a unit volume of porous medium for a unit change in effective stress.
So for water, beta will be mostly maybe 0, I guess, here.
Beta is 1 over Pascal of the units. From memory, it's 10 to the minus 12.
But in multiphase, I think this will become significant because that's air and water, and they might be both compressible.
Yeah, the beta is very small, but the alpha, the most compressible material are clays. And clays, the compressibility can be 10 to the minus 4, 10 to the minus 5. That's why you have land subsidence. in areas with very large clay deposits where the hydraulic head decreases, the pressure decreases. If the pressure decreases, I should have a slide on that, but the effect aquifer that is underneath a large clay deposit, and that happens in several areas of the world. Mexico City is probably the first example. The fluid pressure will start to decrease in the clay. If the fluid pressure decreases, the effective stress increases. The effective stress is the proportion of the weight of the whole material above a location that is supported by the grains, the solids. And if the pressure decreases, the total stress remains the same. There's the same amount of material. So the clay material will start supporting more and more of the weight of everything above, and the clay is super compressible. So that's why you can have tens of meters of compression or subsidence of clay. Is that clear? Okay, and I think that finishes my my section on continuity. So it's very quick presentation, but what I want you to remember is that when you see a partial differential equation for flow or transport in material, porous material, fractured material, think of what the equation represents. It's mass balance. You have the flow terms, mass accumulation term, and mass in minus mass out has to be equal to the change in the mass stored. And I say that also from a numerical modeling perspective. The first quality of a numerical model is that you want to conserve mass. So you want to look at these equations and make sure that your discretization conserves these principles. So the general, we assume here that fluid density, which I had in the last slide, is constant. Again, for most applications that's justified, but not all applications. You might want to keep that variable density term in there. And you end up with a fairly simplified, this is the general form in 3D with I and j varying from x, y, and z. We can simplify if the system of coordinates x, y, and z are aligned with the principal directions of hydraulic conductivity. And in practice, that's what most people do. Unless you have, well, you can still kind of play with that if you have a sedimentary basin and the layers are at some inclination. You just do some rotation of your coordinates and you can align with the principal directions. But this is something that you might see more often, like the 3D form for the case where system of coordinates are aligned with the principal directions. So we have three flow terms. Again, think of these three flow terms as being the mass balance application in x, y, and z, and we have the mass accumulation term. And finally, this equation can be further simplified for a whole lot of different applications. You can simplify it by saying now I have steady state flow. The term here, the temporal derivative would go to 0. If you have flow in the x and y direction only, there's no variation of hydraulic head along the z. The third term here becomes 0. If the system is homogeneous, you could say that kxx is equal to kyy, homogeneous anisotropic. So these terms could be taken out of the derivative, and you might end up with Laplace equation, very simple equation. And that's basically what, when you do graphical resolution of the groundwater flow equation by drawing a flow net in 2 dimensions, you're solving Laplace equation, but you're solving a partial differential equation with lots of simplifications, but you're still solving an equation that is based on the principle of mass balance. This is just to finish here, this is the equation, I call it the Thijs equation, because that's what Thijs solved to represent flow to a pumping well in a constant thickness aquifer in radial coordinates. So you basically can take that equation, simplify it to a much simpler form, which he solved analytically to come up with the Theiss solution. Now, I have some time to cover some, again, basics about fractured porous medium. There's, I'd say, a very large number of approaches for fractured porous medium. I think most people consider that they're a bit more challenging than the granular deposits, although if you work in glacial deposits, they're very heterogeneous. But in the fractured system, it's tricky to come up with a conceptual model that is satisfying, and it really depends on your application. Here I'm talking about flow, but if you go into transport, geothermal energy, multiphase flow, you might want to use different conceptual approaches, not always a single one. But we can go from treating the fractured porous media. I add the term porous because you can consider fractured media, it's only fractures, everything else is impermeable. But you can consider that the matrix between the fractures is permeable, porous, in the more general case. So we can use the equivalent porous medium approach, a discrete fracture network approach. I think you'll see in more detail during these 2 weeks. And multiple continua. And as I've said at the beginning, you could have a combination of these approaches, representing the main fractures individually, representing other parts of your system as dual continuum or equivalent porous medium. So as soon as you have fractured in an otherwise unfractured rock, the hydraulic conductivity increases by orders of magnitude. The analogy we often make is that if you take a fracture that has a thickness of a human hair, its hydraulic conductivity is equivalent of that of a sand unit. So it's unfractured, there's nothing going on, but as soon as you have fractured in a bedrock formation, the hydraulic conductivity increases tremendously, but those fractures have to be connected for a significant flow to occur. The basic equation or relationship that is used for the various approaches, even the discrete fracture network approaches or the multiple continuum, is based on a very simple representation of a fracture as a space between two parallel plates. So we have a matrix here. We have a fracture. It's an open space of uniform thickness 2b or uniform aperture. And if you apply Navier-Stokes equation to represent steady state flow in such a system where you assume that the matrix is totally impermeable, you end up with a very simple relationship for here the permeability of a fracture. It's simply the aperture 2b squared divided by 12. And if we use the same definition of hydraulic conductivity that we had for a non-fractured system, the hydraulic conductivity of this fracture is going to be density times G divided by viscosity. So these are properties of the fluid times 2b squared over 12. And again, that relationship, although we know that natural fractures are not nice parallel plates, they're very irregular, this is used for computing the hydraulic conductivity of a fracture. And if you will have some, like I said, some lectures on discrete fracture networks where you'll see that I know Philippe Davy, he will be generating thousands, tens of thousands of discrete fractures based on some observation. Well, in each discrete fracture, the parallel plate assumption will be made to get hydraulic conductivity, and then he will try to upscale, like knowing the hydraulic conductivity of all these fractures, knowing the connections, basically use a Darcy approach to, about the same as when I showed with the layers, use a Darcy approach where you have these distribution of hydraulic conductivity from the individual fractures and come up with equivalent hydraulic conductivity of these fractures, and then use that at a larger scale for some applications. flow in the fracture is often assumed to be, the porosity in the fracture is often assumed to be 1, so it's an open fracture. But there's some variations that exist. There's applications where people will generate the distribution of variable aperture for a single fracture. There's people who've done measurements in the lab because fractures are not parallel plates, and they will use the same upscaling approaches to get effective porosity for the fracture, which might be different from 1 because fractures might close at some locations, open elsewhere, and get an equivalent hydraulic conductivity for a rough walled fracture. So that's a possibility, but typically in this case we basically assume that porosity is 1, so the fluid velocity in the fracture is equal to the Darcy flux, and it's hydraulic conductivity times the gradient. Relationships have been developed for networks of fractures. Again, these are used for the upscaling as well. So a simple one is we have a set of parallel fractures. All fractures have uniform opening 2B. The spacing is uniform from center to center. It's 2 capital B. And we have these, again, just from fluid mechanics, we have the porosity here of the fracture, the family of fracture is n number of fractures per unit length times the fracture aperture 2B, and the permeability of the ensemble of fractures is n times 2B cubed divided by 12. And again, these are used for if you're interested in flow in individual fractures, but if you are interested in upscaling as well. The fractures are very transmissive. This is from a document that I got from Kent Nowakowski, who worked in the fractured lot for a long time. And we just compare using Darcy's law, using the definition of hydraulic conductivity of a fracture. The transmissivity of fractures is compared to, here we have a fracture aperture. Here we have on the x-axis the thickness of a porous medium equivalent to 1 fracture, and these are lines that show the hydraulic conductivity of the porous medium. And here we take 10 meters of porous medium with a hydraulic conductivity of 10 to the minus 6, so that would be a sandy material. The transmissivity, which is the amount of water that can be transmitted by the porous medium or the single fracture for a given hydraulic gradient, the aperture, is a little bit here, it's a 2.26 millimeters. So it's less than 1 millimeter fracture can transmit for the same hydraulic gradient the same amount of water as 10 meters of fairly permeable sand. So I said various approaches have been developed to look. Yes?
Could you clarify the permeability of the fracture? Is it half the aperture square or the aperture itself square?
This is the aperture. This is the aperture, and if you go back here, you have here the from Darcy's law, you multiply by the thickness here to get, you get hydraulic conductivity, multiply by the thickness, the aperture to get transmissivity, and you would get the flow rate, which would be, volumetric flow rate would be the thickness of the fracture, 2B times Kf times the gradient. And actually, you end up with a 2B cube, which is the cubic law. So the flow rate is related to the cube of the aperture. So for the fracture, the transmissivity is the hydraulic conductivity times the fracture thickness, which is 2B. Yeah, let me go back. So it would be hydraulic conductivity multiplied by 2B, which is the thickness here. That would be the transmissivity. So it depends on the aperture cubed. And if you take a porous medium, the transmissivity is the hydraulic conductivity, and it's shown by one of these lines. So these are 5 different hydraulic conductivities for a given porous medium, and you multiply by the thickness of the porous medium, and that gives the transmissivity. So fractured systems were initially treated with an equivalent porous medium approach at the beginning, but in the 60s already, in the petroleum reservoir engineering, some people were looking at the pressure change in a reservoir that was being pumped, and this is from Kruzman and de Ridder, but actually this comes from the early 60s. Coates derived an approach, the dual porosity approach, Warren and Root. And basically what you have here is on the vertical axis is the drawdown S. The drawdown would be the increase, the initial pressure minus the pressure at some time after the start of pumping, as a function here of the log of time. And this was in a fractured reservoir, basically fractures that are very conductive, but also a matrix that is not necessarily, well, if low permeability, but contains some fluid. And they got this type of response, so linear increase on the semi-log scale of the drawdown, but then some leveling off, and another increase after some sufficient time. So what their concept was that, okay, when you start pumping into a fractured reservoir, the fluid will quickly respond in the fractures, so the pressure will decrease, and you will get this initial behavior. But the matrix contains some fluid. And if initially the matrix and the fractures next to it are at equilibrium, there won't be any flow. But if you start decreasing the pressure in the fracture, because the fracture responds quickly, then there will be disequilibrium, and you will start inducing some flow from the matrix into the fracture. So another source of fluid that levels off here the drawdown. A new equilibrium will establish, and then the matrix and fracture system will behave more like one system, which would be this second part here. So we have a matrix system first, then matrix fracture, and then matrix fracture but behaving as a single system. So they could not reproduce these behaviors with equivalent porous medium approaches, and they started to develop the first models were dual porosity. Warren and Root have developed a model, and this is from Kruzman and de Ridder, but they show this model. We start from a natural fractured reservoir, and from the hydraulic behavior, what they proposed was this type of approach, simplified geometry. So we have a network of fractures in between a matrix that can contribute to flow when there's changes in the hydraulics, for example, pumping in a petroleum reservoir. They proposed, this is the typical Warren and Root approach, so it's like cubic-like, or some other proposed just networks of fractures like this, horizontal fractures with a matrix in between that might participate in flow under certain conditions. Other approaches have been developed where you can even include more types of fractures. So this is from Yushu Wu in JCH, where they introduce a triple continuum approach, represented by it's a bit light here, but you have here some fractures. Some seem to be continuous, forming a continuous path here, and to the left here, vertical fractures with smaller scale fractures here and there. So they say, okay, we could represent this as a network of more continuous fractures, the large fractures, some small fractures here that are not connected, only connected to the larger fractures, but that might contribute to flow or transport. And in between a matrix, that can be porous and that potentially could be permeable, could contain even some smaller scale fractures, so have a non-zero porosity, permeability. And then the other representation, it's a bit more densely fractured, and they imagine like another network of large fractures, horizontal here. So we have horizontal and vertical larger fractures that are well connected with the smaller scale fractures, and they have some fracture spacing here, a capital A for the larger fractures. L sub x would be the typical length of the smaller scale fractures. So they use this geometry then to back calculate using simplified expressions for single fractures or net-water fractures what would be the equivalent properties of these fractures. And they come up with this type of representation. This would be, for example, in a you could view this as what you would have in a numerical model. So you have to assign properties to all your cells or elements. And here, this is only the representation. M is matrix and F is fracture. So in here you would only have the lines are the fractures and the squares are the matrix. So here we would have, it could be a single fracture represented as an individual fracture that is in a matrix that is porous and potentially permeable, or it could also be an equivalent porous medium approach or continuum approach where we have, in this case, mature and fractures are represented by a single cell with equivalent properties. So the properties would be lumped properties of fracture and matrix. The double porosity approach here shows that there's two systems now, the fracture system and the matrix system. So in your model you would have two unknowns for every cell. You would have hydraulic connectivity of the fracture system, hydraulic connectivity of the matrix system. You would have to define properties of your fracture system, but fractures without considering the matrix, and properties of the matrix system. And say you would represent your network of fractures like they did here. Like the properties of the fracture, you would take these, say, vertical fractures, you would compute their equivalent hydraulic connectivity from the simple relationships I showed before. You would compute the equivalent porosity, and those would be the properties of your fracture. And the matrix, well, if it's a rock matrix, if you have properties of the rock matrix, that's what you would use. You would not use properties of the fractured rock matrix, but only the rock matrix. And in this case, what it shows is that there's no connection between matrix block. So there is no flow from matrix to matrix, but there's a connection from the matrix to the neighboring fracture, and there's flow in the fracture network. Dual permeability now, we assume that the matrix itself has some permeability that is different from zero. It could be because of some microfractures. It could be because of some macropores if we're close to ground surface. So in this case, we have, again, the two systems, the fracture media, the matrix media. There is flow in both systems, and there's an exchange between fracture and matrix. And they even introduced this third case, a triple continuum with this intermediate medium, which would be a medium that contains some microfractures. And in this case, there's no flow from the microfractured medium to the next one, but the microfractured medium is connected to the fracture and to the matrix. And you could have, I've even seen a paper where they had the multiple interacting continuum, where you could define if you have large fractures, intermediate fractures, small scale fractures, matrix that is perhaps has some microfractures, you could have more than one, well, several media that are interconnected. Some are not, depends on your conceptualization. But as you can see, this becomes a bit more complex than just porous medium, non-fractured. You can have all these different options depending on your object of your study. And in terms of data need, if I go back to the different systems, so the different approaches, EPM, we have a lumped fracture and matrix system. So basically we only have one hydraulic conductivity and one value of specific storage or porosity. So it's for the combined system. But as soon as you go to the dual porosity, dual permeability approaches, you have to define the fractured medium and give properties. You have to define the matrix medium and give properties. Here in dual porosity, there's no hydraulic conductivity required for the matrix medium. We assume it's impermeable. There's no flow in the matrix, but the matrix can store water. And there's an exchange term that is required. And the exchange term is often based on the geometry that you assume for your system, like these matrix blocks or these parallel plates. Then you can define relationships for the geometry. And the exchange term will be a first order term. Very similar to Darcy's law, because you will assume that there's a hydraulic conductivity in the fracture and a different hydraulic conductivity in the matrix. So there's a difference, and depending on the difference, flow will be from matrix to fracture or fracture to matrix. So you start to get more and more parameters that are required to be defined here when you go to the more complex approach. I haven't talked too much about discrete fracture network, but discrete fracture network, as opposed to the other approaches, and I think in terms of numerical modeling, you will need to identify the location XYZ of individual fractures and also assign the aperture, which could be variable. And in the case where you assume that the matrix is not impermeable or is porous, you will have to define the properties of the matrix. So additional information is required for these individual fractures, but there can be a combination. I think the more pragmatic approach that you will certainly be seeing, at least from Philippe Davy, is that if you can quantify the smaller scale features in your systems, smaller scale fractures, you will use some upscaling approach to get either equivalent porous medium properties or dual porosity properties to put in your model, and the larger scale features you might want to represent as individual fractures. So fracture zones, for example, that are quite thick, because you'll see that from again, a computational point of view, to start putting every decimeter fracture into a model that covers hundreds or perhaps 1 kilometer in scale, it becomes impractical. So you have to be pragmatic, use the information you have, do some averaging at a smaller scale, and try to keep the main feature in your model. I think I'm just about on time. So hopefully this was not way out there or was not too easy for you. I tried to give you a bit of an introduction. If I'll just finish with two references that are still, they're not young, but if you're interested in going from the pore scale to the macroscopic scale, which is the scale of study, Dynamics of Fluids and Porous Media by Jacob Behr, 1972. I think it still is a very good reference if you want to look at these in more detail. I remember when I was doing my PhD, we had the choice between groundwater, which was a very good textbook, but more applied, or people who were not too scared, they looked at Behr, 1972, because it's a bit more advanced, more mathematics, but still very valid. And I wanted to also show this textbook by Guylain de Marcilly, who unfortunately, sadly passed away just last month. It still is an excellent textbook. Also provides some insight into the averaging from the pore scale to the larger scale. Very, very good textbook. And Groundwater is still a classic. It's from 1979. It's available freely groundwater project. Actually, Guylain de Marcilly's book is also available, the full text on the groundwater project website, so you should download it. Freeze and Cherry still is very well written, basic concepts are there. And I want to make a bit of publicity for my friend Alain Darcy, who covers additional topics like geothermal energy, land subsidence that are not in Freeze and Cherry. So some publicity for my friend. And the last thing, it's an anecdote. If you look at the cover of Groundwater, and Al Freeze once told me where the cover came from and how it ended up being like that. That's the anecdote. So they had a graphics designer to do the cover, and Freeze and Cherry, they have in their textbook this Therrien flow system. Joe Toth was a hydrogeologist, spent his whole career in Canada in Edmonton, and in the early 60s, he came up with this concept of flow systems. So this is a cross-section that could be very deep. You have local flow systems here, intermediate and very deep flow systems. And Al Freeze said that they had this is a figure 6.3 in their textbook, and they gave that figure to the graphics designer. Well, that would be our cover figure. But the designer decided it looked better the other way. So he basically put it upside down. I think the authors were a bit upset at the beginning, but they got used to it and now they like it. So that's it for me. Thank you for being, for listening, and I'll be happy. I'll be around for until Friday. I'll be happy if you have any question about what I presented. I did not talk much about my research, but like I said, a couple surface, subsurface flow modeling. I've worked in fractured rock, non-fractured rock, probably all kinds of stuff. So I'll be happy to have a chat if you are interested. Thanks. I don't know what the plan is, but I can certainly make my presentation available. It's on some downloaded.
In any case, you've been recorded.
Yeah, that I know, but perhaps they don't want to listen to me again for an hour and a half.
Thank you very much. So if you have any questions, don't hesitate to ask.
Oh, I've got one for you if that's fine. At the very beginning, you had a diagram with REVs. Practically, if you're working with a system, is there a way to tell if your domain is the right size to be an REV, or if you're working with something too big or too small? Do you just guess that you have it?
You know what? I did not mention it, but we know that the concept of REV exists. But in practice, I think there's very few people who going to say, okay, do I have an REV here? You kind of go intuitively. Of course, if you go from the pore scale to, say, a hand sample or a column sample, then you assume, okay, I've got my REV. But we know that when we start to go at a larger scale, the assumptions we make for the representation of our, say, layer might not be valid anymore. And there's discussions, I did not mention it, but there's a trend now to do more and more modeling at very large scales, continental and even global scales models. And there's people who say, well, does Darcy's law apply at a kilometer scale? What is the REV at that scale? And I think these are interesting questions. I'm not sure I have answers, but it's something that we kind of take for granted, and probably if, again, I'm talking more from a pragmatic, practical perspective. What we do often when we have applications, we want to study a system. Eventually, we want to characterize the system, measure properties, and use some type of modeling approach for our system. Could be very simple or more complex. And what we try to do is reproduce observations. And if we're able to reproduce observations, knowing that our model is far from being perfect, there's more than one model that will reproduce observations, Then at least we try to look at uncertainty, and maybe that's where we could find out that, well, my model just does not represent what I observe, so there's something wrong with the approach, the equations, perhaps this concept of REV at that scale does not apply, but it's, it would be a good discussion, perhaps my colleagues here at the front have, Danny probably has something to say.
I don't have answers, I just want to make, can I, Rene?
Yeah, please.
So this is a very good question, but the REV concept also varies with the property. So especially related to the talk of Rene about discrete fracture, flow and discrete fracture. So while the REV for porosity can be a few cubic centimeters, you can increase the sample, you're not going to get different porosity. When you increase the sample of fractured rock, this is based on modeling and some measurements, the REV for discrete fractures can be in the order of many cubic meters of rock samples. We're talking about more than 10, 20, 30 cubic meters in which you can start to characterize the behavior of that formation in terms of discrete fractures. So REV is not only related to just any arbitrary volume, but also to the property that you're looking at. So fracture flow would be a good example of huge REV. Cyprien, do you agree?
I agree. I mean, that's also why we have this multi-continuum concept as well.
Yeah, you probably will hear about dispersivity in the next presentation, I assume. And dispersivity is, okay, there's this concept that it increases with scale. But dispersivity really arises from heterogeneities. And if we were able to represent at a very small scale the heterogeneity of a system, say at the field scale, you want to simulate transport of a contaminant over 100 meters, and if we were able to have such a characterization that every square centimeter or very small volume you have the hydraulic conductivity, you put that into your model, you will not use values of dispersivities of meters. You would use very small scale, but what happens is that often you don't have that luxury of having a very small scale description of hydraulic conductivity, so you use some equivalent hydraulic conductivity, and then you have to jack up dispersivity because like the average velocity you get from your homogenization, the fluctuations around that average will be huge, which you represent with dispersivity. And again, it's like Danny mentioned, you're looking at another process where the REV for flow might be okay, but for transport, you might be off.
If I can add something, so I have an expert, so I will touch on dispersivity a little bit. I just wanted to say later in the week, I think next week actually by the end of the course, Marco Denz will talk about stochastic upscaling. I want to really touch on that. So something that you can do sometimes is when you don't really have an REV, for example, for velocity, you can still get away with having representative statistics for velocity. So you can keep more information by keeping the fluctuations in terms of statistics, even if for the average you don't quite have an REV. So sometimes you can kind of save the REV concept, even if it doesn't really work. Other times, yeah, you just have your properties scale with scale, and that's the practical approach and works reasonably well, so you have to live with this.
So I have actually this, correlated approach to the discussion is interesting. But when you're talking about REV, so let's say if there is a larger fracture, cannot we use Darcy Brinkman there rather than just only Darcy? Because Darcy has some assumption about this REV, but if there are large fractures, their flow could be literally taken to the Brinkman term.
Yeah, well, I'm not sure I understand, but the like for Darcy's application to fractures, I mentioned that fractures as small as say 1 millimeter will have a significant impact on flow, but velocity will never reach the limit.
If the system dissolves, then the fracture will eventually go bigger, and then it's not really the porous medium anymore, right?
Yeah, if you've ever visited the karstic system, I've visited the karst, and the openings can be a meter large. So you get free surface flow in there, and the REV concept kind of breaks down. And Darcy's law will not be valid. That's why I say that some people have developed relationships where you have Darcy's law, Q is equal to K times the gradient. They will have an exponent for the gradient to account for the fact that there's no longer a linear relationship, and you get some turbulence as well. But that would be a very specific system in the karsts, which are, I say fractured rock are not easy, but karsts are an order of magnitude more difficult. So I tend to stay away from karsts. Yes?
I had a question about when you talked about the flow velocities, the Darcy velocity divided by porosity, but porosity can also have dead end curves. So how do you show that without having it incorrectly account for the dead end curves that are?
Yeah, I mentioned that porosity, its definition, it's for the whole volume of porous medium. It's the volume of pores or voids for the whole volume of porous medium. And you could go out in the lab and measure that. But then you could take the same material, put it into a column, and run a tracer experiment. And then if it's controlled, you get your breakthrough. And you might try to fit the breakthrough, and no, you can, from the breakthrough curve, you can get the arrival time of the center of mass of your tracer, which is actually an indication of the velocity. And you might find out that, well, if I use the lab porosity that I got, it doesn't fit. I have to use a lower porosity, and then this concept of dead-end pores would play, because in your material you might have some pores that are, I don't know, better connected, conduct more flow. The tracer will preferentially migrate through these pores, and the tracer will go into the dead-end pores and not. But actually, the breakthrough curves would show other signs as well of that. But that's this concept of dynamic. People use different words: dynamic, kinematic porosity, which is the proportion of porosity that really contributes to flow. But it's I would say it's a concept that is real, but to measure it, to come up with values is tricky. Yes?
Thanks for the presentation. So, how do you choose for your models natural boundary conditions? Like, what's the way to proceed in order to not just impose mathematical valid boundary conditions, but such conditions that they fit well, because of course you will simulate on a finite domain and you have to somehow guess correctly, or how does it work? How do you choose your boundary conditions?
You mean for say a general application at a catchment scale, or
no matter what you want to simulate? I mean, you presented the Darcy's law basically, but you have to impose some boundary conditions. And how do you choose them in such a way that they become natural, so they don't influence your simulation in an unnatural way? Yeah. How do you choose your boundary conditions for whatever simulations you are doing?
Okay.
Because of course there's an impact.
Yeah, that's a very good question. You try to choose as much as possible natural boundary conditions, which would be contacts between low permeability and high permeability systems. So, like if you do 3D modeling, the base of your model probably will be some perhaps bedrock that is not very fractured. So okay, this will be impermeable. And then you have to, on the sides, decide, okay, this might be a water divide or another contact. And then at the surface, well, you have the surface network, drainage network that you will represent in some way. And of course, if you're simulating, I say we do a lot of catchment scale. Well, we have the atmospheric boundary conditions. So rainfall, snow melt, snowfall, snow melt, and so on. I'd say the top surface is not so, I won't say it's not so difficult. You still have to make choices, but as soon as you do some subsurface modeling, like it's not a guess, but you have to use your best judgment, and ideally then you would have to change the boundary condition. I'm just, one of my master's students is just finishing, and he has this cross-section, a 2D cross-section, and the outlet is a lake, and there's a highway near the lake, and they're using road salt, and the salt goes into the lake. But he generated a larger scale 2D cross-section, and he was not too sure, well, what should I have at the lateral boundary on the left, the right, the bottom? And he actually tried different things. He tried incoming regional flow, I assume it's about that, fixed hydraulic head, uniform hydraulic head, impermeable, and then he compared his results. He was focusing on the lake. He compared the results, and he found out that, well, the further away boundary did not make much of a difference on what he was observing, but it was our best educated guess because we didn't really have data. It's tricky, but it's very, I would say it's very important because your boundary conditions drive your system. And you have to make the most reasonable choice based on what you know of your system. And then, like I said, ideally test, okay, what if it was not this? What if it was this other type of boundary? Do my results change dramatically or not? Yes?
Just a brief comment about the inertia effect. In my opinion, you kind of mentioned that maybe Darcy's law only breaks down in karstic systems, but I think many of recent studies show that inertia effects does matter at much lower Reynolds number, like centimeter per second. So that's something I will talk about. I think it's important to be aware that it's not the only in karst system that Darcy is covered.
Yeah, that's a good comment. Yeah.